Hey, welcome to The Explainer. Today we're going to pull back the curtain on something super important in the world of AI, how we actually figure out if a model is any good and how we make it even better. All right, let's just jump right into it. Picture this. You spent weeks, maybe even months, building this incredible AI model. It's finally up and running. But how do you really know if it's any good? More importantly, how do you make sure it stays good over time? Well, one of the biggest hurdles you're going to face is this thing called model drift. The world doesn't stand still, right? People change how they shop, new trends emerge, the economy shifts, and a model you trained on yesterday's data can become totally useless tomorrow. It's kind of like trying to navigate a city with a 5-year-old map. Good luck with that. So, how do we fight this drift? How do we make sure our AI is trustworthy? We need a solid toolkit. We need a way to constantly check in on our model's performance to see what it's getting right, and maybe more importantly, where it's messing up. Okay, let's start with a really common type of model, the classification model. These are the ones that basically make a yes or no call. Think, is this email spam or not spam? Or is this credit card transaction fraud, or is it legit? And for that job, our absolute go-to tool is something called the confusion matrix. Now, I know the name sounds a little intimidating, right? But trust me, it's actually a super simple but really powerful way to get a quick snapshot of how well our model is doing by comparing what it thinks is happening to what's actually happening. It's really just a simple little 4-box grid. It lines up with the model predicted against what actually happened. This lets us see not just if the model was right or wrong, but how it was wrong. All right, first box, the true positive. This is the home run. The model screamed fraud, and guess what? It was actually fraud. Perfect. A direct hit. Then you've got the true negative. This is also a big win. The model saw a perfectly normal purchase and correctly said, nope, nothing weird here. It did its job by leaving the good stuff alone. Okay, now for the mistakes. First up is the false positive. This is your classic false alarm. Your model flags a totally legitimate transaction as fraud. You know the feeling, right? Your card gets declined when you're buying groceries. It's annoying for the customer and creates headaches for the business. And then there's the one that really keeps data scientists up at night, the false negative. This is the worst-case scenario. A real, honest-to-goodness fraudulent transaction happened, and the model just missed it completely. It slipped right through the cracks. That's a huge problem. So when you look at these 4 squares together, you start to see this fundamental tension. It's a constant balancing act between 2 really important ideas, precision and recall. Let's use a spam filter as an example, because it's perfect here. What do you want more? Do you want high precision, where your filter is super cautious and never ever throws an important email from your boss into the spam folder? Or do you want high recall, where it's like a super aggressive guard dog that catches every single piece of spam, even if that means a few of your newsletters get flagged by mistake? See the problem? It's a trade-off. So let's break that down. Precision is all about quality. It asks the question, when my model does sound the alarm, how often is it actually right? High precision means when it speaks, you listen, because it's not crying wolf. Recall, on the other hand, is all about quantity. It asks, of all the actual fraud attempts that happened out there in the wild, how many did we manage to catch? High recall means you're not letting much slip by. So how in the world do you balance these two? They're often pushing in opposite directions. Well, that's where this handy little metric called the F1 score comes into play. It's a clever way of combining both precision and recall into a single number. Think of it as a grade point average for your model's performance, giving you a much clearer picture of how it's really doing. Okay, so that's classification, yes or no. But what about models that predict an actual number? Let's switch gears and talk about regression models. These are the ones that try to predict things like how much will this house sell for, or what will our sales be next quarter? And for these kinds of models, just saying it was wrong doesn't really cut it, right? We need to know how wrong it was. I mean, if you predict a house price and you're off by $500, that's amazing. But if you're off by $500,000, well, that's a total disaster. So one of the most straightforward ways to measure this is with something called mean absolute error, or MAE. It does exactly what it sounds like. It just tells you, on average, what your margin of error is. So you might find out that, on average, your predictions are off by about, say, $10,000. Super simple, really easy to explain to anyone. But what if some mistakes are way worse than others? That's when you bring in the root mean squared error, or RMSE. It has a neat little trick. By squaring the errors, it punishes the really huge, embarrassing mistakes a lot more heavily. It's extra sensitive to those big misses. All right, so we know how to grade our models. We can tell if they're doing a good job or not. So what's next? Well, we improve them, of course. This is where we get into optimization, basically tuning up our model's engine to get every last bit of performance out of it. A classic method for this is called grid search. And honestly, it's kind of a brute force approach, but hey, it's thorough. You basically make a list of all the possible settings, the knobs and dials of your model, and you tell the computer to just try every single combination. It's slow, but at the end, you'll know for sure which combo was the absolute best. But yeah, grid search can take forever. So for those who want to be a bit smarter and faster, there's a more advanced technique called Bayesian optimization. Instead of trying everything blindly, it learns as it goes. It makes an educated guess, sees how it does, and then uses that result to make an even smarter guess the next time. It's all about zeroing in on the best settings way more efficiently. And you know, all of this, the constant measuring, the metrics, the endless tuning, it all leads to what might be the single most important lesson in all of AI. And it's this: building a model isn't something you just finish. It's not a one-and-done job. It's a continuous mission. If the rules of the business change, if customer behavior shifts, your model will fail to adapt unless you do something about it. That's why you have to constantly retrain it with new data. This whole cycle, evaluate, optimize, redeploy, repeat, it's not optional. It's absolutely essential if you want your AI to stay useful and trustworthy. And that kind of leaves us with one final big question to chew on. We know that the AI that's woven into our daily lives is constantly being tested and graded. But is it always being graded on the right test? When we choose between precision and recall, are we making the choice that's actually best for us? It's definitely something to think about.